Okay, let's suppose that this block I'm drawing is the inverter. Okay, so the switch mode DC to AC power converter. So we have here, remember, the voltage source inverter. So it is a converter that has the input voltage constant. Then we have some set of control signals. And here we have the output. Suppose that is not, let's say, the limitation, but here we are discussing, for example, one phase inverter, okay, just one output, and at this output you have V naught and high naught as voltage and current. Okay, suppose also that V naught and I naught are already demodulated, so filter out, and so these quantities are sinusoidal quantities. Okay. V naught, I naught, sinusoidal. Typically, these, for let's say, driving electromechanical actuators, the load is represented by the winding of the motors that can be modeled typically by an inductance in series with a resistance. Okay, so the resistance models the ohmic losses in the windings, and the magnetic, say, behavior of the circuits is modeled by the inductance. Okay, so typically the load for this kind of application is an ohmic inductive load. So the load is ohmic inductive. Okay, so this means that if you look at the voltage and the current waveforms, we have that voltage, for example, is something like this. And the current is sinusoidal, but the current is characterized by the phase shift. If the load was a pure inductance, then the shift was 90 degrees. So the current at the output I naught lags the voltage by exactly 90 degrees. So it starts here. Okay, but since typically we have an ohmic inductance load, the phase lag is a little bit lower than 90 degrees. So we consider that, for example, we have this. Excuse me, just 1 minute. Sorry for the break. I have visitors in my office, but no problem. So the current is something that has a lag which is, say, less than 90 degrees. So it is something like this. Okay. For example. And so this is the current I naught. Okay. So what we can say about this typical behavior of the output voltage and current after the modulator in our inverter, that we can distinguish between 4 phases basically. Okay, there is a interval in this the period in these waveforms in which both the voltage and the currents are positive. Okay, let me call this as number 1 interval here. Okay, this interval is represented in this way, in which both the current and the voltage are positive. What does it mean? That if you look at the power at the output of the circuit, the power which is, say, that transitates outside the inverter, then this power, which is the product of these two quantities, is a positive power. Okay, so in that specific situation, the inverter provides power to the load, and so in that case, we are in what we call the, say, motoring operating mode. Okay, this is the forward motoring properties. Okay, then we have, for example, another intervals. Let me see this one. Okay, in which the current is positive, but the voltage is negative. In that situation, the number 2, we have a voltage which, as say, is reversed, so it is like this one. Okay, the power provided to the output is not, say, positive, it's negative, so the power is absorbed. Something like, let's say, here. So in that specific case, my inverter operates as something that accepts energy, power provided by the load. That situation we have in a, say, braking operating mode. This is the reverse braking. Then there is a third situation, that is this one. And the third situation here, both the voltage V0 and the current N0 are negative. So that means that here you have the current entering here. The current is, the power now is positive because it's a product of two negative quantities. So we have again a situation in which the inverter operates as a motor, but now is a reverse motoring operating mode. And there is another situation, which is the third one, this one, in which you have the voltage which is positive, but the current is negative. So a situation like this. The power, again, is a power which is absorbed, so the power is entering the inverter. So we have again a situation in which we are operating the inverter in a braking operating mode, and this is the forward braking. Okay, so what happened here is that you have in a, say, Cartesian plane like this one, in which you can plot the voltage V0 and the current. The situation are the one, the second one, the third, and the fourth. Okay, so we have the motoring here. The motoring are the situation number 1 and the situation number 3. Okay, in which the power provided is positive, and then you have the braking. So in the situation in which the inverter operates as a motor, providing power to the load, that the inverter operates exactly as is intended, so as an inverter. In the situation 2 and 4, in which you have, let's say, the power which is absorbed by the inverter, and so we have the voltage or the current which are negative, what happens that the inverter is no more, say, something that we can continue to call inverter, but basically this is a rectifier. Okay, so these 4 quadrants in which you have, let's say, the possibility to operate the inverter, say, in these 4 quadrants of operation, suggest that we are searching for a circuit, a switch mode power circuit, in which you can have bidirectional current and reversible voltage. And so, which is the best circuits that we already discussed, in which you can have this four-quadrant operation for the voltage and current, is the switching power pole, the four-quadrant switching power pole, so the full bridge. Remember, the circuit, which is built by having two legs in parallel, an input voltage source, and a current I naught in this way. This is the leg A, this is the leg B. This is the bipositional switch that can be replaced by using, say, two switches, as we already know. This is the unitary switching function QA, and this is the unitary switching function QB. So this circuit here exactly make it possible to replicate the four-quadrant operation I just discussed in this way. Okay, so let's discuss something that basically we already learned in previous lecture. So the four, but now we have some difference due to the fact that the output voltage is a sinusoidal one, which is the four-quadrant switch mode converter. The first thing that you have to understand that in that situation, which I'd like to have as an output sine wave, we need to consider as pulse width modulator triangular voltage, which is the carrier of our modulator, plus a control voltage, which is a sine wave. So differently from what we learned in the DC-DC converter, now we need a control voltage, which is a sine wave. So we control is a sine wave. For example, let's suppose that we have this waveform here. This triangular voltage is our triangular carrier that you have inside the pulse width modulator. Okay, this peak value is the triangular peak voltage. The frequency is the switching frequency of our converter, and then we have the control voltage, something like this. Let's suppose that the period of this sine wave as a control voltage is T1. Okay, this is a DC quantity, and then you have something which is, let's say, goes up and down these DC quantities, this like an offset, and this is the AC contribution. The peak value of this AC contribution is this one, is V control peak value. Okay, so we can say that the V control voltage is the sum of a DC contribution, and about the DC contribution, we have to say that in order to maximize the say AC variation of the sine wave, this DC contribution is exactly F, the peak value of the triangular voltage, okay, plus the AC part, which is a sine wave having a peak with the control peak, sine wave omega 1 t. Okay, this is my control voltage here. So this is the description of the control voltage we need for this inverter. Second point that we already discussed is that the frequency f1, which is exactly the frequency of the control voltage of the sine wave, should be well less than the switching frequency. This because basically we are using say modulator. Okay, so we are say, using a variation of the duty cycle at the exit of the modulator, which replies the information that we have in the control voltage. We amplify this kind of say, information, and then we get something at the output that we need to demodulate, so we have to filter out. Okay? This kind of construction make possible to reconstruct, to reobtain the information at the beginning of this chain, so the information that we have inside the variation of the control voltage, only if you respect the Nyquist theorem. And the Nyquist theorem says that the switching frequency should be at least 2 times the bandwidth of the signal I want to reconstruct. This is a sine wave, so the bandwidth is, say, the sine frequency, so 2 times f1. Okay. Typically, in order to make easy the demodulator effect, so the filtering at the output of the inverter, because typically the demodulator is the motor itself, so we are using the inductance and the resistance of the motor as a low-pass filter, the switching frequency should be much higher than the frequency f1 of the control voltage. Okay, so this is what we already know in order to respect Nyquist problem. If we respect this consideration, the output after the demodulator free which is a low-pass filter, the output voltage that is extracted from this low-pass filter is an average voltage, which has a peak value and has the same frequency of the input. So basically, this is the we can say, we can put in this form, V01 is the fundamental component of the output voltage. So now the one here exactly defined the order of the output of harmonic that we can get. And so the fundamental component of the output has the same form of the control voltage. Okay, so this discussion was basically the same we had for the DC converter, in which at the output after the demodulator we have the filtering of a square of a rectangular waveform, and the average of this waveform is a DC quantity. Okay, that has the same information that we had for the control voltage. That case was a DC quantity. Pay attention that here the average sign here is a moving average. So this V not average is not a DC quantity. Okay, it's just the average any over any TS period, okay, of the switching. It's something that can change period by period, okay, because the control voltage is something that as a modulation changes. So it is not a DC quantity, it's a quantity that has this variation here. That later on we can see some waveform that say explain graphically what I'm saying now. Basically, this process that starts from a modulator, a pulse width modulator that make possible to convert information that are in the variation of an analog signal into the variation of a width of a rectangular signal, so the pulse width modulation, and then it's amplified and then filter out to obtain the variation you have at the beginning is something that we already discussed about the DC-DC converter. So here we have our full bridge that can be employed to do this kind of operation. So let me discuss this in the usual way. So the leg A, okay, so TA plus, TA minus, dA plus, dA minus, this is the node A. This is the leg B with dB plus, dB minus, this is the node B. And so we have the current port here. This is the voltage port, which we have CD, VD. Here we have a current, I naught. Then you have here a voltage, V naught. This node is called N. So remember that V naught is VAB, VAN minus VBN. So it's the difference between the output of the two half bridges. Okay, so the same happens for the moving average, VAN minus VBN averaged. Remember that VAN for an half bridge is simply the product of the duty cycle by which I'm switching the transistor in the leg A multiply the voltage constant at the input. VBN averaged is the same product by dB multiplied VD. My assumption is that duty cycle of the leg B is simply 1 minus duty cycle of the leg A. And so we have that V naught averaged is dA VD minus dB VD. So it is 2 times dA minus 1 VD. Okay, so remember that this is the standard expression of the voltage V naught that we already had for the DC 4-quadrant converter. Okay, dA ranges from 0 to 1, so V naught is something that ranges as an average value from negative VD to plus VD. The duty cycle can be derived from this expression here, okay, from this one. The duty cycle JA is equal to 1F plus V naught averaged over 2 times VD. And now suppose that we are operating the pulse width modulator of this 4-quadrant converter into its linear operating mode. Remember what is the linear operating mode. Basically, if you have this control voltage, okay, if we have an amplitude modulation factor, which is basically 2 times the control voltage peak, so this is the peak to peak. Sine wave of the control voltage by the triangular peak, which is less than 1 or even equal to 1. So that means that the dynamic of the control voltage is always inside the dynamic of the triangular voltage. So we are in what is called the linear region of our modulator. Okay. If you are in the linear region of our modulator, then we can express the transfer function of the modulator in this way. We have that dA over V control is 1 over VD Ri peak. So V control is dA multiplied V triangular I. Since I'm just considering the duty cycle A, let me put this as V control A, the control voltage for the leg A, okay? Exactly in the same way we did for DC for quadrant converter. Now I have this expression. This expression here, dA is here, so we can say put dA there. So we can have that V control A is V triangular peak divided by 2 plus V triangular peak value 2 Vt multiplied V naught average value. Okay, so basically this is the same steps we had for the 4-quadrant DC-DC converter. Now let me put V control A minus V here, and then we have just this expression. So basically I just rewrite the previous equation in this way, because now look at this part. This is the total control voltage subtracted by half the triangular peak value. Let's have a look at this expression, okay, that I have here. Basically, this difference is the difference you have here. If I subtract the total control voltage by half the triangular value, which is the DC quantity, I just have this part here, which is the AC contribution of the control voltage. Okay, so this one is V control A peak sine omega 1t. So we have V control A peak value sine omega 1t, which is equal to V triangular peak divided 2 Vd multiplied the average value of the output voltage V naught. Okay? But the output average value is something that we can describe in this way, because this is what I want, is a sine wave having a peak value and a behavior like a sine wave. So we have V naught sine omega 1t. Okay, so basically we can say that we have this contribution here, then we have the same contribution here. So this description, say this quantity, can be eliminated, then we have just the peak value. V control voltage of the leg A peak value is V naught peak value multiplied V triangular peak 2 times Vt. Now remember our definition of the amplitude modulation factor, which is given here. I define the amplitude modulation factor as the ratio between the peak-to-peak value of the control voltage, the sine wave, divided by the peak value of the triangular voltage. So if I put the number 2 here and I divide by VTRI peak, this is exactly MA, the amplitude modulation factor. So at the end, we derive that the amplitude modulation factor of our inverter is exactly V naught over Vd, or in other term, the peak value of the output fundamental component is given by MA multiply VT. Okay, MA is the amplitude modulation factor. This amplitude modulation factor depends on the amplitude of the control voltage with respect to that of the triangular voltage. Okay, it can ranges from 0 when the control voltage is, let's say, has no amplitude. Okay, is a DC quantity, or can be equal to 1 when the dynamics of the sine wave is exactly the dynamics of the triangular voltage. Okay, so we have two different situations. Let me call this case. In one situation, for example, here, when the sine wave has this behavior here, so it reaches the peak value, okay, VT Ri peak is the same of 2 times control voltage peak, then MA is equal to 1. Okay, so I have the maximum possible dynamic of my control voltage. Otherwise, it happens that when the control voltage is, let's say, constant here, so you have no amplitude in that situation, V control peak is null and MA is 0. So depending on the amplitude of the control voltage, we can range this MA from 0 to 1. So basically, we can use the amplitude of the modulation of the control voltage to get different value of the output fundamental component of the output voltage of my inverter. Okay, and these are amplified by the voltage VD. Typically, this can be shown also in a graph in which you have V naught fundamental component peak value over VD as a function of the amplitude modulation factor. The amplitude modulation factor ranges from 0 to 1, and so we have that behavior. So this means that at the maximum, when MA is 1, the peak value of the fundamental component of the output voltage is exactly VD. And you cannot exceed the voltage VD at the maximum output voltage. This region in which you have a linear variation of the output fundamental component peak value versus MA is called the linear pulse width modulation. Okay. We investigated all these, say, operation of the inverter just looking at the duty cycle DA, okay, and so just looking at the, say, the leg A of my full bridge, okay. So I'm just, say, discussing this one. What about the leg B? But at this point of the discussion of the course, this is not a surprise to discover that for what concerns the leg B, we have the two different modulation techniques that we already had for the 4-quadrant DC-DC converter. Remember, unipolar pulse width modulator or bipolar pulse width modulator. So for the leg B, we have the unipolar pulse width modulator, or 3 levels PWM, or you can have the bipolar. Two-level PWM. Which is the difference between the two? Well, basically this is something that we already know, because we need just one control voltage, okay, for my full bridge inverter. So my pulse width modulator here needs just one control voltage, just one sine wave to be compared inside the pulse width modulator with a carrier, which is a triangular waveform. And so these exit with a QA and a QB unity switching function. One is the signal commanding the transistor TA plus, and the other one is the signal commanding the transistor TB plus. And then we have also the logical inverted signal QA minus, which is 1 minus QA, or QB minus, which is 1 minus QB, commanding the low side transistor. Okay, so we need just one control voltage instead of having two different control voltages. So typically what happens is that I have the control voltage for the leg A, and I'm using this control voltage as a total control voltage. Okay, so here we have the control voltage, the total control voltage, the wall control voltage I need is the control voltage of the leg A. But from this control voltage, I can derive the control voltage for the leg B as V triangular peak value minus the control voltage. For both the leg A and the leg B, the rules that I am following for the generation of the two unity switching functions, QA and QB, are the classical standard control voltages. When the standard rules, when the control voltage is higher than the triangular voltage, the unity switching function is 1, otherwise it will be 0. For the bipolar, again, I have that the total control voltage is the control voltage for the leg A. What about the control voltage for the leg B? Even the control voltage for the leg B is the same of the control voltage. Pay attention that now the rules by which I generate the switching function QB by comparing the control voltage B and then triangular voltage is opposite that I'm going to follow for the control voltage A. Okay, this is the standard definition that we already know. So basically, we found out the same conclusion that we already discussed for the DC to DC 4-quadrant full bridge converter or H bridge converter for the inverter. Okay. What I want to stress here that my output is no more a DC quantity. The output at the end of the modulator will be a, say, sine wave having the same frequency of the control voltage and having an amplitude which can be derived simply by using this linear relationship here. No, B naught, big value, MA multiplied. So it's something that can be modulated. So if you want to change the frequency of the output, basically you have to change the frequency of the control voltage. If you want to change the amplitude of your output fundamental components, you have to change the amplitude of the control voltage through the amplitude modulation part. So this is the means by which I can modulate output voltage amplitude and output voltage frequency. This is something that I request, okay, something that from a fixed DC quantity VD make possible to generate an AC waveform which is totally controllable, okay, in amplitude and in frequency. Let me just share the slide, okay, because in the slide there is a drawing which is much better than the standard drawing I can draw myself, okay. So let me, you should see this page of the slide number 6 that you have. because this slide show you, for example, what happens for the unipolar pulse width modulator. Okay, this is the behavior in the waveforms for the modulator, which we have the triangular waveform, okay, VTR, and the two control voltages for the leg A and the leg B, and the unit switching function and the output voltage. Okay, so pay attention that here the triangular waveform has has no DC value. Okay, so for example, the axis here is in the between, is exactly here. Okay, in my discussion, the triangular voltage is totally positive, but the discussion is the same. Okay, forget this axis here, horizontal axis, and suppose that my axis is, let's say, at the bottom here, and the discussion is exactly the same. So we have a triangular waveform having a peak, which is the triangular peak value here, at V triangular peak divided by 2, which is now this line here. We have the control voltage A. The purple one is the control voltage A. Remember that this control voltage A is also the overall, the whole control voltage for my full bridge. Okay, so when I compare the control voltage with the triangular waveform, what happens that my modulator generates the unitary switching function QA with the standard, say, generation low. When the control voltage, for example, here in this interval is higher than the triangular voltage, we get 1. When it is lower, you get 0, etc. As you can see, depending on the amplitude of the control voltage, the width of my unitary switching function pulses is different. So the amplitude is modulated, is sine wave modulated, because the control voltage has exactly a sine wave behavior. Okay, so we have a very large duty cycle when the control voltage is, say, higher. We have a very small duty cycle when the control voltage is less than half the triangular peak value here. And what happens when the control voltage crosses V triangular peak divided by 2? The duty cycle is almost, say, 50% here in this part. Basically, we have a sine wave modulated pulse width waveform. Okay, this is the unitary switching function. When you multiply the unitary switching function by the voltage VD, you get the output voltage VAN. Okay, so the coding function here, ranging from 0 to VD, is the voltage VAN. So the output voltage is instantaneous voltage at the output of the leg A. What about the control voltage for the leg B, which is the green one in this slide? But this can be obtained by the control voltage, the purple one, simply by the difference between the peak value of the triangular voltage minus the total control voltage. So remember what I said about the DC-DC four-quadrant converter. In that situation, unipolar pulse width modulator, the control voltage for the leg B is the symmetrical waveform with respect to V triangular peak divided by 2 of the control voltage of the leg A. And you can see this graphically by the green curve here, the sine wave, which now is the control voltage for the leg B, which is symmetrical with respect to the V triangular peak divided by 2. Now I have to compare the triangular waveform with the green V control B waveform with the standard generation low. For example, when the green control voltage V control B is higher than the triangular waveform, for example, here you get 1, 0 otherwise. Even here you have this, say, for the voltage VBN, the standard sine wave modulated rectangular waveform. Of course, we have a phase shift because they are shifted by 180 degrees, the two control voltages. And so when you get the difference, you get the red one. And the difference between VAN and VBN is the output voltage V naught. This is the instantaneous voltage you get at the output. It's not the modulated one. So remember what happens in the unipolar pulse width modulator, something we discussed for the DC-DC for quadrant converter. It happens that when the control voltage is higher than the V triangular peak value, the total waveform of the output is positive. And this happens, for example, in this part, in this first part here, because the control voltage, the purple one, is higher than V triangular peak divided by 2. When the control voltage is otherwise less than V triangular peak divided by 2, the total, the whole output voltage is negative, okay, because it's a unipolar pulse-width modulator. And this happens in the second half of the period of the voltage V0. The red one is exactly the output waveform. What we can say about the output waveform? But the standard consideration that we already had for the DC-DC for quadrant converter. The switching frequency of the output waveform is twice the switching frequency of the switch. Okay, you can see that here in one period of the voltage, say of the triangular voltage, you have 2 pulses. So the frequency by which you have the commutation of V0 is twice. So that means that in terms of harmonic components, we have harmonics at 2 Fs and not at 1 Fs, for example. The red waveform is the waveform that we have to filter out in order to derive which is the in order to filter out the, say, the fundamental component. And the curve that you have superimposed onto the red V0 waveform here, the blue curve here, I cannot recognize easily the color, but the sine wave you can see here, V01, is exactly the fundamental component of the red one. This is my output voltage after filtering out the red one. And this is what I can get at the output, can get at the output for an inverter. The frequency of this fundamental component is the same frequency of the control voltage. So if you want to change the frequency of the output waveform, you have simply to change the frequency of the control voltage. Remember that this frequency should be well less than the switching frequency. If you want to modulate the amplitude of the output fundamental component, you have to modulate the amplitude modulation factor. So you have to change the amplitude of the control voltage according to the law I provided you before, V0 peak product of MA multiplied VT. Okay, unipolar because you can see that for each half of the period of the output voltage V0, you have just unipolar voltages. Okay, what kind of transistor, what kind of say sequence of the operation are involved, but the same sequence of the switches that we already discussed for the 4-quadrant DC-DC converter. Okay, let me share the whiteboard here. Okay, you should remember that for positive output voltage, the transistors that are involved are something like TA plus, TB minus for having V0 equal to VD. Then we have TA minus, TB minus for having 0. Then we have again TA plus, TB minus to get VD. And then you have TA plus and TB plus for having 0. So this happens for, say, T1 divided by half on the first half of the period. Okay, you have this sequence of switches and the output voltage as, let's say, VD and 0 levels, totally positive. Then for the second half of the period, you have something like TA minus TB plus, and then you have TA plus TB plus, this for having negative VD, 0, and then TA minus TB plus for negative VD, and TA minus TB minus for having 0. So this is for T ranges for T1 divided by 2 over T1. Okay, so the sequence are exactly in the same say form, the same sequence that we have already discussed. Okay, and so also the devices that conduct the current follow the same pattern that we discussed and analyzed for DC-DC for quadrant converter. Nothing new. Okay, this is for the unipolar pulse width modulator. This is unipolar because for each half of the T1 period, you have just positive or negative output voltage. Is at 3 levels because you have one level which is VD, the second one which is 0, and the third one which is negative VD. What about the output spectrum? Let's have a closer look to the output spectrum. Of the voltage V0. This is the output spectrum of the red curve I show you in the slide. Okay, the red instantaneous voltage V0, which is twice the switching frequency, etc. For sure, we have an harmonic component which is at frequency F1. This is the component at the same frequency of the control voltage. Okay, so F1 is exactly 1 over T1, and this appears in the output spectrum. Then I have, remember, typically, so I'm drawing now the typical waveform that you can have, generally speaking, then we can cancel out some harmonics. You can have something at the switching frequency, something at twice switching frequency, harmonics at third switching frequency, etc. Okay, so you have all the fundamental component of the switching frequency. And harmonics. Of the switching frequency, this one, etc., etc. Then you have intermodulation products. So something that is related to the fact that you have F1, okay, and a switching frequency Fs. The modulation brings you some intermodulation products. For example, you have around Fs, you can have, I don't know, this one, let me change the color here, you can have Fs plus F1. So this difference here is exactly F1. This one is Fs plus 2F1, etc. Or here you can have Fs minus F1. So there are a lot of harmonics that are spaced by the F1 frequency with respect to the harmonic or the fundamental of the switching frequency. Fs minus 2F1, etc. The same happens around 2Fs, something like this. So for example, you can have 2Fs plus F1, 2Fs plus 2F1, 2Fs minus F1, etc., and also around 3Fs, etc., etc. Okay, these are called, also these quantity here are intermodulation products. These intermodulation products have frequency F H, for example, which are K times Fs plus or minus N times F1. Okay. This axis is in frequency. Remember that we have the amplitude modulation factor definition. So amplitude modulation frequency modulation factor. MF, which is Fs over F1. Okay, is the definition, is defined by the ratio between the switching frequency and the output frequency, so the frequency of the control voltage. So for example, I can also describe the same behavior, the same axis here, in terms of the ratio between F and F1. So I can rescale my horizontal axis. Instead of having the frequency, instead of having something which is dimensionless, which is F over F1. For example, here, which you have Fs over F1, this is exactly MF. This is 1. This is 2 MF. This is 3 MF. And for example, in terms of subharmonics, this is MF plus 1. And then you have MF, let me put here, plus 2, etc. Okay, rescaling, you can have this kind of horizontal axis. This is a generic representation. What happens for unipolar pulse width modulator? For the unipolar pulse width modulator, first of all, we have a switching frequency of the output which is twice the Fs frequency. So let me put A V naught as a repetition of 2Fs. So what does it mean in terms of the output spectrum? That in the output spectrum you have no Fs harmonics, okay, but you have also, say, no the third harmonic, not the fifth harmonic, etc. So no odd harmonics. Since my switching output frequency is 2 times Fs, you can have also 2Fs, you can have only 2Fs as a fundamental, and then you have harmonic of 2Fs. So you have 4Fs, and then you have 6Fs, etc. But you have no odd harmonics. Okay, so let me use, I don't know, the purple one for this A. So it means that, for example, you cannot have this one. Let me dash it here. You cannot have this one due to that. The second characteristics that we can exploit is a characteristic that we can call B, that happens on this. The first one, A, happens naturally, comes naturally from our construction of the modulation. Okay, the point B happens only if the modulation frequency Fs over F1 is an even number. If MF is an even number, we can have two, say B1, for example, two consequences. The first one is we have no intermodulation products around odd harmonics. No intermodulation products around odd Fs harmonics. What are the odd harmonics? For example, Fs is an odd harmonics. Okay, so it means that we don't have any of these quantity. No intermodulation products around this. Or here. The second consequence is that, let me call this B2, is that you have no even harmonics of Fs. Blue. So for example, it means that you have no even harmonics, so you have not these two FS harmonics. So as you can see here, there is a lot of simplification in the output, say, spectrum of the voltage V naught, especially if you have a frequency modulation factor which is an even number, because you get F1, which is the frequency you want to get at the output, but then the first high order harmonic is something around 2fs, which is, let's say, quite spaced from F1. And this typical spectrum is something that can make easy the filtering and the modulation of the output voltage V naught. For example, using simply the filtering action of the, say, motor winding, the inductance and the resistance of the motor winding. Let me share with you a slide that you have in your, say, bunch of slides, number 6 here, showing exactly the spectrum for a voltage, for a unipolar, pulse width modulator. Okay, this is exactly obtained by the construction I gave you before. That situation, we have exactly MF, which is an even number, is an even integer here. You have the axis is scaled with F1, so it is F over F1, exactly the second scale I explained you before. So we have the harmonic, which is amplitude is 0.8. 0.8 means that my amplitude modulation factor MA is 0.8, so 80% of the dynamic of the triangular voltage is occupied by the control voltage, for example. I can modulate this value by MA. Then the first harmonic is something around 2 MF. There is no around the MF frequency, or the switching frequency, but you have something here. Okay, no around the other harmonics, but you have something the even harmonics here. So you can see the output spectrum is not so populated by harmonics, making easier the filtering of this quantity. Or the high order harmonics. What about the bipolar? Let me just discuss the construction of the bipolar waveform. For example, here, bipolar pulse width modulator is obtained by a construction in which both the control voltage for the leg A and B are the same. Okay, and they are the wall control voltage provided at the input of the modulator. In this slide, again, we have the triangular waveform that has a switching frequency, TS or T-switch, as indicated here. And then you have your control voltage, which is a sine wave. We are talking about linear modulation, so the amplitude of the control voltage is within the dynamic of the triangular voltage. So it does not exceed the maximum amplitude of the triangular voltage as indicated here. And then we have to use this control voltage both for the leg A and the leg B. Okay. So, for example, here, when the control voltage is higher than the triangular voltage, you get 1. Okay. For example, here at the beginning, or otherwise we'll get something which is 0. The control voltage for the leg B is exactly the same, but now the generation of the unitary switching function should be is, let's say, opposite. Okay, so you have to follow the opposite rules. So it means that, for example, in the first interval you get 0 and not VD. When you get the difference between the two, you can obtain something like this. The output voltage, which is VAN minus VBN, now is totally bipolar, ranges from minus VD to plus VD. So the blue curve here is the output voltage V naught, not filtered yet. As you can see here, there is no situation in which you have totally positive voltage or totally negative voltage, like in the unipolar one. You have just two levels, minus VD or plus negative VD or plus VD. And modulation, the amplitude of the width is sine wave modulated, okay? as you can see in the waveform. The orange curve here is the fundamental component of this curve. So something that you can obtain when you filter, low pass filter this blue curve. Okay, you can obtain the fundamental component. Okay, no, nothing new with respect to our discussion we got for the DC-DC for quadrant converters. Let me share the whiteboard. What are for the unipolar, for the bipolar parts with modulator, the sequence of transistors that are switching? But according to our description already had for the 4-quadrant DC-DC converter, we get just two different switching action that are TA plus and TA minus on, followed by TA minus, TB plus on, etc. So there are two different, say, switching action. Okay. Basically, the two transistors, TA plus and TB minus, and TA minus and TB plus are operated just they were a single switch. There are no, say, too much the complication we had for the unipolar pass width modulator. We have just these quantities for any time interval in T1. So the output voltage will be VD here or negative VD here. What about the output spectrum? Let me just redraw the general spectrum you can get at the output when you have a rectangular waveform that you have to filter out. You have, let's say, V not 1. You have the F1 component. The amplitude is MA VD. Then you have something around Fs, something around 2Fs, something around 3Fs in terms of an axis scaled in frequency. If you want an axis scale in F over F1, then you have 1, you have MF, 2MF, 3MF, etc. This is the fundamental of the switching frequency, the second harmonic, the third one. Then you have intermodulation product here. Something like this. So what happens for the bipolar pulse width modulator? For the bipolar pulse width modulator, first of all, we have to say that the output frequency is something that, let's say, changes, the output voltage, sorry, changes with the same frequency of the switching frequency. It's the same as Fs. So we have the elimination of the odd order harmonics, for example, as it happens for unipolar pulse width modulator. But basically, remember that FH, which is the intermodulation order, is K, Fs plus minus and F1. So what happens in that specific situation when you get the Fourier transform of that waveform I showed you before for the output voltage is that intermodulation products only exist if K plus N is odd. For example, this is Fs plus F1. So it means that 1 Fs plus 1 F1. So the sum of K and N here is 2. So this quantity here does not exist. This harmonic does not exist because the summation is even. The same happens here. Here we have 2fs plus f1. So now k and n is odd, so it exists, but it does not exist this one. Okay. 3 plus 1 is even, so it does not exist. So we can eliminate a lot of intermodulation product, and we eliminate all the intermodulation product in which k plus n is even, if you want. This is the basic consideration, the basic, say, simplification we can have that comes out naturally from our construction. Then there is another one, they call B, that only happens if the frequency modulation factor, Fs over F1, is an odd number. Because in that specific situation, no even harmonics of Fs. Even harmonic of Fs, for example, this one is eliminated. And so, for example, the 4 Fs is eliminated, etc. Okay, so let me share the slide in which I have the spectrum. Is this one. Here there is an example in which MF is exactly an odd number, is 15, as you can see here in this caption. MA is 0.8, and so this is the reason why the harmonic at frequency F1 reaches exactly 0.8. Then you have the first bunches of harmonics around Fs. The second one is not MF plus 1, but it is MF plus 2, because the first the harmonics you have in between is eliminated, because it's another is something that has, let's say, even k plus n. Okay, the even harmonic here, 2fs, is eliminated because you have MF, which is another number, etc. If you compare this spectrum with respect to that of the unipolar one, okay, with that we have before, for example, we have a very big difference in the presence of harmonics around MF. Okay, previously here you have no harmonics around MF, so it means that the first high order harmonics in the unipolar one is something around 2fs, while here you have to pay attention to the harmonics around MF, around Fs. So it means that the filter reaction here is not so effective with respect to that you can have in the unipolar one. But this is comes as not surprise, because it's the same effect that you have in the 4-quality converter. Okay, we computed the maximum ripple for unipolar and the bipolar pulse width modulator in that situation. Okay, and we compare what happens in these two situations. We learned that the output ripple for the current flowing to the inductor for the unipolar one is, say, a half that you can have in the bipolar one. Okay, having the same, say, filtering at the output, because this happens as a result of these harmonic, this spectrum contribution at the output. Okay, questions, doubt, problems, whatever? Something that is not clear? Okay, before starting the next discussion that requires some, say, derivation, I think that is best to stop here, okay, just to not interrupt my, say, discussion. So we can restart next Tuesday morning, okay? Of course, if you have questions, I can, say, answer your question here. Otherwise, I like to thank you for your attention, and we can see each other next week. Thank you. Bye.